Electron configuration. This is the next subtopic. Electron configuration is where a lot of students get stuck. It's a pretty difficult concept, so I'll try my best to make things super clear and easy to understand. Let's begin. Before we get into learning about orbitals, we need to have a clear understanding of the underlying concepts. First, we all know what energy levels are. We say that electrons are found in these energy levels. However, we can divide these energy levels into sublevels. Each energy level is divided into sublevels, which consists of four main types: S, P, D, and F. And these sublevels contain a fixed number of orbitals. For example, the S sublevel contained 1 orbital. The P sublevel contained 3 orbitals. The D sublevel contains 5 orbitals. And the F sublevel contains 7 orbitals. Now, what are orbitals? Orbitals are a region of space where there is a high probability of finding an electron. Each orbital can hold a maximum of 2 electrons of opposite spin. As I mentioned in my previous videos, the vocabularies highlighted in yellow are frequently tested by IB. So IB might ask for the definitions of these terms. Keep this in mind. Let's take a look at the shapes of specific orbitals. The S sublevel contains 1 orbital and it has a spherical shape. The P sublevel contains 3 orbitals and they have a dumbbell shape. You should know the specific shapes of these orbitals, as IB might ask you to explain the shapes of the orbitals or ask you to personally draw them. Now, let's take a look at electron configuration. Electron configuration is used to describe how electrons are distributed in its atomic orbitals. 3 rules are followed when writing electron configurations: the Aufbau principle, Hund's rule, and the Pauli exclusion principle. The Aufbau principle states that the electrons fill the lowest energy orbitals first. The Hund's rule states that when filling degenerate orbitals, which are orbitals with the same energy, electrons fill all the orbitals singly first. And lastly, the Pauli exclusion principle states that any orbital can hold a maximum of 2 electrons with opposite spin. These 3 rules will be applied when writing down the electron configurations of particles. Electron configurations can also be illustrated in 3 ways. Number 1, full electron configuration. Number 2, condensed electron configuration. And number 3, orbital diagram configuration. Now, this is a picture of a periodic table with the corresponding sublevels labeled. You can notice that the main group elements are S and P block elements. Also, you can see that the transition metals are D block elements. Aufbau principle states that electrons fill the lowest energy orbitals first. This image shows the order of fill of electrons into the orbitals, as it orders the orbitals from lowest to highest energy. Now let's look at the order of fill more closely. In the first line, you can see the notation 1s2. The number on the left-hand side, 1, shows the current energy level. The letter S indicates the particular sublevel, and the number 2 on the right-hand upper side shows how many electrons are occupying the orbital. As you can see, the first energy level only occupies 1 sublevel, 1 orbital, and so can hold a maximum of 2 electrons. Now let's look at the second line. The second line shows the different sublevels that are occupied in the second energy level. In this case, there is an addition of the P sublevel. The P sublevel holds 3 orbitals, and each orbital can hold a maximum of 2 electrons, according to the Pauli exclusion principle. So, the P sublevel can hold a maximum of 6 electrons. In total, the second energy level can hold a maximum of 8 electrons. The third line shows the different sublevels that occupy the third energy level. In this case, there is an addition of the D sublevel, which holds 5 orbitals that can hold a maximum of 2 electrons each and a total of 10 electrons. This third line shows that there is a total of 18 electrons that can occupy the third energy level. The fourth line shows the different sublevels that are occupying the fourth energy level, and you can see that there is an addition of the F sublevel. The F sublevel holds a total of 7 orbitals, which can hold a maximum of 14 electrons. Now let's talk about the order of fill. After writing down the different available orbitals in each energy level, we can draw diagonal lines through them to see the order of fill. By following the diagonal lines, we can see the order of fill. First, 1s2 becomes filled by the electrons, then 2s2, 2p6, 3s2, and then 3p6, 4s2, and then 3d10. We can see that 4s2 becomes filled before 3d10. This is because 4s2 is in a slightly lower energy state than 3d10. It would be nice to memorize the order of fill for your test. However, if you forget, you can quickly write down the orbitals and just cross diagonal lines through them like the picture above, and that will quickly show you the order of fill. Okay, let's look at an easy example. For your test, you will be given a periodic table, so don't worry about that. Example 1, oxygen. If you know its position in the periodic table, you can straight away say that it's a p block element. We are going to write the full electron configuration, the condensed electron configuration, and the orbital diagram configuration of oxygen. The atomic number of oxygen is 8, so we know that there's going to be 8 protons and 8 electrons that make up oxygen. Before I write down the configuration, I want to quickly draw some diagonal lines to remind myself of the order of fill. So I'm going to write down the different sublevels and draw diagonal lines through them. Now I'm ready to write the full electron configuration. The full electron configuration would be 1s2, 2s2, and 2p4. This is because there are 8 electrons that make up oxygen. We know that 1s2 is the electron configuration for helium. So when writing the condensed electron configuration for oxygen, we can write it as bracket of helium 2s2, 2p4. For the orbital diagram configuration, you need to start off by drawing the different orbitals that are involved. They should be in order, according to the order of fill, and they should be drawn in a ladder format to show the differences in their energy state. So, there are 2 electrons that can fill up each orbital, and they need to be in opposite spin. So you need to draw that accordingly. And for the p orbitals, you need to make sure to fill them up singly first due to Hund's rule. Stop the video and try magnesium and magnesium ion on your own. Magnesium is an atom with 12 electrons, and before I write down the configuration, I would like to write down the order of fill on the right-hand side just to keep me reminded and help me when I'm writing the configuration. The full electron configuration of magnesium is as shown above, and this will total up to a total of 12 electrons. Because I know that 1s2, 2s2, and 2p6 is the electron configuration of neon, a noble gas, I can put that in brackets next to 3s2 and write down the condensed electron configuration of magnesium. Now, orbital diagram configuration. I will plug in the electrons with opposite spin accordingly to get the orbital diagram configuration of magnesium. Magnesium 2+ is an ion of magnesium as it has lost 2 electrons, so there will be a total of 10 electrons. I'll write the order of fill on the right-hand side again as a guidance. The full electron configuration of magnesium 2+ will be as shown above because it has lost 2 electrons. This full electron configuration is the same as the electron configuration of neon, and that will be our condensed electron configuration for magnesium 2+. The orbital diagram configuration, again, will show how the electrons are occupied in the orbitals of magnesium 2+. Last one. This is a bit complicated. First, stop the video and try chromium and copper on your own. Okay, these are exception elements. Their electron configurations show irregularities. IB explicitly mentions these elements and frequently tests them. So I want every one of you to know how to write the configurations of chromium and copper by heart. Again, this is very, very important. Let's first look at chromium. Looking at the periodic table, we can see that the atomic number of chromium is 24. So 24 electrons will occupy chromium. Now let's write the full electron configuration of chromium. Students will typically fill in the electron configuration of chromium like this. However, this is incorrect. The D sublevel becoming half full or completely full is more energetically stable than filling up the 4s orbital and making the last d orbital empty or half empty. So its electron configuration will actually be written like this: 4s1 and 3d5. Now looking at the periodic table, we can condense their electron configuration as argon, 4s1, 3d5. The orbital diagram configuration will be drawn as shown above. We will fill in each orbital like this. However, instead of filling up the 4s sublevel with 2 electrons and the 3d sublevel with 4 electrons, we would like to only put in 1 electron in the 4s sublevel and put the additional electron in the 3d sublevel so that each orbital inside the 3d sublevel can have 1 electron each. This half-filled 3d sublevel is energetically more stable. Next question. Looking at the periodic table, we can see that the atomic number of copper is 29. So there will be 29 electrons that will occupy copper. The full electron configuration of copper is also easily mistaken. The full electron configuration written above is incorrect. Instead of writing 4s2, 3d9, we write it as 4s1, 3d10. This is because having a half-filled or fully filled d sublevel is energetically more favorable. Next, condensed electron configuration. The full electron configuration of copper up to 3p6 is the electron configuration of argon, so we can condense the electron configuration of copper as argon 4s1, 3d10. For the orbital diagram of copper, we're going to again fill in each orbital with its electrons of opposite spin. However, instead of filling up the 4s sublevel with 2 electrons and the 3d sublevel with 9 electrons, we're going to fill in the 4s sublevel with 1 electron and the 3d sublevel with 10 electrons. That's it for topic 2. I'll see you in the next topic.